Good evening and greetings, Submariners. Welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as we do every night during Advent of Code, we're going to be working through the night's puzzle drop in C++. Thank you all for watching. If you're watching the live stream on Twitch, you can check out the Twitch channel description, and there you are going to find a link to my YouTube channel where we have replays of all the previous day's puzzles, and you'll also find a link to the GitHub repository where I upload all the code that we write in these sessions. If, on the other hand, you're watching later on YouTube, just check the video description right down there, and you're going to find links there both to the Twitch channel for the live streams, and once again to that GitHub repo where we upload all of the code. So we are really getting into the home stretch of Advent of Code right now. We have just about 3.5 minutes until tonight's puzzle drops, and just 4 more days of puzzles to go. So we're definitely in the section of puzzles that are kind of like interesting, tricky, maybe a little complicated, maybe some ways to get tripped up. I think so far probably the hardest, definitely the one that we spent the most time on, was this day 19, this beacon scanner where we had, in three-dimensional space reconstruct the position of all those scanners and all those beacons to map out the trench we were diving into. Last night's about about this dice game was pretty interesting, and I think that we had like good algorithmic insights about it. But if you watched last night's stream, you saw me make a couple of silly coding mistakes that slowed me down. But the basic idea of the algorithm was good. So who knows what we'll see tonight? We might find ourselves a real stumper, and I might have to, pause and step away and, come back and try again later. I don't promise on these streams that I won't sometimes be completely stumped. You never know. But I will do my best, and we'll see what we can accomplish. Like I said, we're in the more difficult puzzles right now. Although day 25... usually is something a little different, a little wacky. Like last year, I think day 25's puzzle was pretty easy. And, you got the second star just for having unlocked all the previous stars. The year before that, 2019, it was a little adventure game to play that you could just play in the little ink code interpreter for the little toy computer that had been built up in previous puzzles that year. So... who knows what these next few days will hold. But we'll find out soon, at least for tonight. So you can see that I've already set up the basic skeleton of a program for our solution for tonight's puzzles. This is just a bare-bones C++ program. It does nothing but return 0 to the calling environment. But it does include the check and IO libraries that I've written that are in my repository here that we use to do things like assertions and reading from file input, because we use those pretty much every day. So we might as well include them ahead of time. And I've also set up this build file that tells the Bazel build system that we're using how to build the program. So I just specify the name of the program, the source code files, in this case it's just one file, and its library dependencies here. And then you can see that I've already, built and run it here, and it just does nothing, which is what we expect right now. We have just about 10 more seconds to go till we get tonight's puzzle. Away we go. Reactor reboot. Operating at these extreme depths has overloaded the reactor. It needs to be rebooted. Core is made up of a large 3-dimensional grid, made up entirely of cubes, 1 cube per integer 3-dimensional coordinate XYZ. Good thing we have a 3D geometry library written, isn't it? Each cube can be on or off. Start the reboot process, they are all off. You know, not old reactor you've seen before? Oh, yeah. Look at a reactor from last year. To reboot the reactor, you just need to set all of the cubes to either on or off by following a list of reboot steps, your puzzle input. Each step specifies a cuboid, the set of all cubes that have coordinates which fall within ranges for x, y, and z, but they turn all of the cubes in that cuboid on or off. For example, given these steps, x from... Okay, so we have x, y, and z ranges here, and whether to turn them on or off. The first step on turns on a 3x3x3 cuboid. Okay, so these ranges are inclusive. That's good to know, consisting of 27 cubes. Second step turns on a cuboid that overlaps with the first. So only 19 additional cubes turn on. The rest are already on. Third step turns them off. Final step turns on a single cube 10, 10, 10. After this last step, 39 cubes are on. Okay? The initialization procedure only uses cubes that have x, y, and z positions of at least -30 and at most 50. For now, ignore cubes outside this region. Okay. Got a larger example. Last two steps are outside. Others are fully within it. So the last two, for now, we're supposed to be able to ignore cubes outside of the region. Execute the reboot steps. Consider how many cubes, considering only the region, minus 50 to 50 in the three coordinates, how many cubes are on. Okay, let's get the input. I strongly suspect that part 2 of this puzzle is going to ask us to work with a region beyond that 50, that, you know, plus or minus 50 in each dimension, but we will find out. So let's look at what the input looks like. And, okay. Yeah, so it's, well, I think I saw, okay. All right, so first thing we'll do is just to have a little struct that well, we're going to use my dimension grid library for arbitrary geometry. We'll just say using AOC 2021 dimension, well, 3. Maybe we'll just call that grid 3 for three-dimensional. Okay, so we're going to have a struct that represents a procedure. And in there, we're going to have a bounding box in this x, y, and z that is going to be an orthotope. Which is just a fancy word for a hyperrectangle, basically. And bool for on or off. And then we can write parse procedure which to return a procedure parsed from its line representation. So I am going to use a regular expression to do that from the RE2 library. Because I think that that is going to be simplest. So we'll just say, we'll do static lazy RE2 pattern. So this lazy RE2, basically it gets parsed and compiled the first time that it's accessed, and you never have to pay for it again. So we'll say we'll use R strings here, regular expression, because that'll make it a little bit easier to write. So the first one will be on or off. We'll just say some word-like characters. X equals then maybe a minus, and then some digits. And then we're going to escape those dots because dot otherwise just matches any possible character in regular expression syntax. And then it'll be similar here. You're watching me write regular expressions live, which is, can be dicey, folks, but hopefully I'll get this right here. Okay, we've got that for y, and then a final comma, and same thing for z. Format that more nicely. So we'll check RE2 full match. That line, that pattern, and this box here is going to be, it's going to have min and max points in it. So we'll say box parsed dot box dot min point dot coords 0, which is the x coordinate, and then we'll have the maximum x coordinate will be the same thing at the max point, and then it will have the same thing in y and z, which are coordinate indexes 1 and 2. So I'm doing a lot of copy pasting here to go kind of fast, but we changed that to 1, 1 for the y dimension, and 2, 2 for the z dimension. And we'll format that heinous long line there. And, oh, you know what? We also, though, need to parse on or off as a string view. So we'll put that in the, that will actually be the first thing that we parse, on or off. If on or off equals on, then parsed dot on equals true. Else, if on or off is off, parse dot on is false. Otherwise, there is some kind of parsing error. So we will check fail in that circumstance, but then we will return the parsed instructions. So now let's go ahead and read in all of those procedures. So first thing we'll do is just read lines from the file. We'll get a vector of strings for each of the lines. Come on. I want strings. Include string. Okay. And that's we're gonna use our read lines from file function. Sorry. We need to actually name that variable, don't we? Lines. We'll do read lines from file, argv1 for the first argument to the program, and then we'll just build up a vector of procedures, so procedures. So for each of the lines and lines, we will and place back on that, we'll parse a procedure from that line and put it on the list of those procedures. Now, we do need to kind of clamp these regions, at least for part 1 here. we need to be able to clamp these regions into rectangle into the minus 50 to 50 range in each dimension. So I think the simplest way to do that is we'll just write a method called clamp on procedure, and it will return a new procedure that is clamped to that region. So basically, if for d equals 0 to 3, which is the number of dimensions that we're working with, if just well, let's see. I guess if the box is completely out of range, then we don't want to consider it at all. Because the way that I've written this box code is that even if it's 0 dimension, even if it's, you know, like 0 in every dimension, it can still cover 1 point because the min point and the max point are the same. So I'm going to have this return an optional procedure because if everything is completely out of range, then yeah, we'll say, so if box dot min point dot chords d is greater than 50, then we'll return null opt because the min point is already out of range. And similarly, if the max point is less than -50, then it's completely out of range in the other direction. So there's nothing to do there. But then we'll say procedure clamped, make it a copy of this. You don't necessarily have to do that. We'll say clamp.on equals on. We certainly want that to be the same. And then for each dimension of the box, we'll put it in here. So we'll say clamped dot min point is the coordinates at that min point are the, because we still want to consider the parts that of you know, these big cubes that are not cubes, orthotopes, or, you know, rectoids or whatever that do overlap with the plus or minus 50 range. Although it kind of seems like we only really have to consider up through here, and everything below here is out of range in one of those dimensions, but we'll see. Clamped.box.minPoint chords D will be the larger of the actual min points coordinates at that and -50. You not like this? Okay, we need to do this as int 64t so that max is okay with that. And then similarly, we'll clamp the max point so that the max point doesn't go above 50. And that we will do min over max point. We will return clamped. Okay. Now, we can, we'll just, I'm going to use a sparse representation because I feel like it. And we will say, we'll just use a flat hash set of points, which represent those cuboids. And then for procedure, in procedures, if, well, so first we get the clamped version. So, if there is no clamped version, if it clamps down to nothing, then we just continue. But if clamped is on, then we will insert in our set all of the points that are in range of that bounding box. And I've already written iterators for that box class that iterate over all the in-range points. And I haven't tested them, though. You know, they could be incorrect. But otherwise, we erase everything in that range. And I think, can we give it a range of iterators to erase? Will it play nicely with that? No, it won't. Okay, so we'll have to do that one by one. So for those points in the box, we will erase them if they are to be set off. Okay. And then the number of cubes that are on is the size of that set. Now, maybe we should have used a dense representation, but I'm using a sparse representation, and I think the problem is small enough that that will still be fine. So we need to add all of these dependencies to our build file to be able to build and run this program. So we need to add dimension grid. We need RE2 and flat hash set and strings from abseil. We don't need flat hash map right now, but we do need the abseil strings library. I think that's all we need. So let's go ahead and try and run this with our test input and see what it looks like. No guarantees, as usual, that I haven't made a mistake, but we will see what it gives us. Okay, it didn't build, so that's one thing. Let's see. Do you not like matching, putting this into a string view? Well, if you insist, I can make that a standard. I can make that a string for on or off. Let's try again. Okay. There's something wrong with the iterators in our dimension grid, so let me just get down to 481 where that's a problem. Const iterator, did we forget to make this? Yeah. Oh, it should be friend class orthotope, not friend class rectangle, because we decided to use a fancy name for it. Try again. We're getting close with all these errors. LG 430. Point does not provide a subscript operator. Well, I'm not asking it to use a subscript operator. I'm trying to subscript. Oh, chords. I see. Min point dot chords. That's see all kinds of errors that I had in my little dimension grid that I'm only finding out now. I'm actually trying to use it. But now we've got an answer after fixing all that stuff in my library. Let's see if it's correct. Okay, it is not correct. Well, let's use this big example and see as a test and see how far we get. So I'm going to go ahead and copy that and put it in, call it test.txt. And let's run our program on that test. Okay, so it's giving us a different answer, a wrong answer apparently. Well, let's go back to our program here and let's just print out what it thinks all of the point elements are in here that it's putting in the first time, just to see if that looks correct. So we'll just say if first time, we're going to set that to false after we do the printout, but for const point and p, sorry, grid 3 point and p in clamped, in the clamped box, you will print out a debug view of that point. Okay. Might be pretty big, but we'll, see everything. Okay, we're seeing a lot of coordinates, and then it runs and it finishes. So, so these should be x, y, z, and immediately this seems wrong. The iterator behavior seems wrong. So let's look at how we implemented the iterator on orthotope here. So we go through the dimensions. Oh, I guess we try and we do, yeah. Even then, is the clamping wrong? Yeah, something is obviously wrong from the jump, because we're going from -11 to 8 in the z dimension, and I don't think any of these are that. Let's see if we just parsed that stuff correctly. Maybe we didn't. print out the min and max points and just see if if this will help tell us if it's like some parsing or clamping problem, or it's a problem with how we iterate and generate those points in the box. Actually, I should have cleared that out first so that we can just zip. Oh man. Oh, so we just, ate up our whole output. Well, still. Oh, it's going up to 8. It should only go up to 7. Okay. So I think it's overshooting. Now the middle one only goes up to 17. The first dimension goes all the way to touches. Okay, so I think that just it is an iteration problem. I see now, but let's just get rid of that. And just for my own edification, I want to make sure that it parses min and max correct. So min is minus 20, minus 36, minus 47, and max is all that good stuff. But yeah, this this is not proper iteration. We are we are not generating the points in the grid properly with these iterators. So the way that this works is we go through. Maybe we're not setting end properly here. Yeah, okay. Give me a sec here. Well, here, I'll just say. It's the last one, then we're going to have it be otherwise, we will have it be just that value from the min point. Well, I do have a nice way that we can check this, actually. Well, maybe. I'm not sure. Let's just see what this does anyway. Those min points and max points are correct. I still want to print that stuff out the first time, actually. Because we'll see if towards the end it gives us something that looks like it makes sense. Yes, and it gives us the correct answer for part 1. So it was that enumerating the points in the orthotope that was the problem. So we can now get rid of this debugging statement here and run it on our actual input for day 22. Okay. Now let's see if that's correct. All right. That's part 1 done. Now that the initialization procedure is complete, you can reboot the reactor. Now run all the reboot steps for all cubes in the reactor. We have a huge number. just a giant thing. Um, so now we have to figure out. Oh boy. Hmm. We need to figure out, I think, intersecting regions of these cubes, and be able to, like, sum up volumes of on and off, because we cannot afford to keep track of individual points in here anymore. The numbers are too big. So this is kind of another exploding solution problem. So first thing I'm going to do is just make a commit with our part 1 solutions. Day 22 part 1 solution. I'm going to go ahead and copy the part 1 source code, and we'll use that as the basis for part 2. Yeah. So, even if you like take a bite out of one of these orthotopes or hyperrectangles, or not exactly cubes, you what you wind up with is at worst you're going to end up with like 7 remaining well, I guess the on parts can overlap as well. So we need to sort of invent or discover or look up maybe like some of these solid geometry algorithms, because obviously if like regions don't intersect at all, that we're turning on and off, it's no problem. It's very easy to deal with that. But if they take chunks out of each other, and I guess like a cube can be fully within another cube, and yeah, it can be a mess. So oh boy. I mean, we're going to have a set of these orthotope boxes. That's for sure. And we need to figure out how to intersect and subtract them, basically. So, and we should probably do that in the actual library. So let's go into Dimension Grid here, where we've defined this orthotope class, and I think I don't know that we necessarily need. Well, we need intersection for subtraction probably, but like the union of 2 orthotopes is man, some number of things. Oh god, this is okay. Well, first thing I'm going to think about is just say that we have 2 cubes that are or orthotopes that represent on cells. How do we compute the union of them so that it comes down to like just non-intersecting orthotopes? So I guess we'll write a method here called like union. Makes sense, right? And it will be some number of these orthotopes. I guess the other thing to think about is No, I think this is okay. How many steps are there in this puzzle, I wonder? Day 22 TXT. There's a fair number of those. I do kind of wonder if this is simpler than it looks because, like, so I'm seeing on. Oh, okay. Oh no, now I'm seeing off. I was beginning to think, like, oh yeah, this is going to be so easy if it's only turning stuff on the outside, but no, there are off as well. There are many on instructions, but then there are a mix of on and off. So maybe so I mean there's some techniques from computer graphics here that I don't fully remember, but I'm thinking about things like binary space partition that you can, divide space up by planes essentially. I'm just gonna look that up on Wikipedia. You can join me in reading about binary space partition. Yeah, use. Ugh. So I see an article of computing the volume of the union of cubes. It was published relatively recently. Oh boy. You're gonna have to read this whole paper to understand this is the question. You can see here. Oh boy. Well, we can definitely use that algorithm if it comes down to it, but man. I mean, I'm seeing that, people have definitely approached this problem before, but I don't want to just Well, okay, let me think about it. Okay, the union of two cubes. I guess if you just have like edges scrunched together, then that would be like possibly up to 8 cubes that you could represent the union of two cubes as, and as little as one. Um, and as far as turning things off, like subtracting things out from cubes, um, at worst that takes a bite out of the edge of a cube, and you're left with 7 cubes. So I think yeah, I'm gonna try and figure out. Like, I'm gonna try and do like this union and subtraction stuff. So let's go ahead and start thinking about it. Um, well, so actually, in writing union, it might actually be valuable to first write an intersection routine. So that's so because the union of two cubes is just the two original cubes if they have no intersection. So so for each dimension, the min point is going to be the largest of the min points of the input. So it's going to in that dimension, we're going to have the largest value from the min points of the two. So so do max of of point dot chords at D and other dot min point dot chords at D. And then for max, we'll have the smaller of the two maxes. That should be the min of the maxes, I see. If the min, is greater than the max, then, there's no range where they overlap. So we would return null opt. But if all that works okay, then we can return that intersection. And first thing I want to do is just to do a bit of a safety check on this. In part 2 here, we're, not really doing anything of import here, but I'm just going to compute the intersection of a couple of cubes. So we can just say grid 3, not actual cubes, orthotopes. I realize I'm using cubes a little loosely here, and I shouldn't, but we can say a dot min point. Well, we'll have the min point for a be the origin, but we'll say a dot max point will be chords is, we'll say 1, 2, 3. Actually, yeah, we'll do 1, 2, 3. And then for B, B dot min point, we'll say is 0, 1, 2, and B dot max point can be something really, well, relatively big. We'll do 999. And we will then say intersection is a dot intersection B, and then we will just print out what the intersection, well, so first we'll check intersection dot has value, and then min, we can print out intersection min point, and do the same for max, and then that will just give us an indication if our logic for computing intersections at least is correct. So going to go ahead and run part 2. It'll still parse the input even though it doesn't really matter. Actually, we need to add a build target for it. So we'll just copy and paste what we have for part 1 to get our start for part 2. Okay, so does that look correct? Yeah, so go from 0 to 1 in x, from 1 to 2 in y, and from 2 to 3 in z. Yeah, that all looks correct. Yay! Okay, so intersection seems to be working properly, at least for that one simple test. Okay. Next thing we need to do is union. So well, the other thing, I guess the other thing we could do is keep track of all the on stuff. Well, I wonder how far we could get with just doing these intersections, because the way that I'm thinking about it is we can compute the all of the pairwise intersection between things that this is getting a little the way that I was thinking about doing it is we could just keep a list of everything that has ever been turned on, but that is not going to be tenable. That's not going to work, I don't think. I think we actually want to be able to compute unions here. So okay. So first thing we'll do is try and find the intersection. So and if there is no intersection, then the union is just the two original orthotopes. So auto, well, standard optional orthotope intersection equals intersection with other. If there is no intersection, then we can just return the two orthotopes as they are. Otherwise, we need to cut something out. So I think that we should, just as a heuristic, leave the largest volume cube intact and make the cutout from the smaller volume cube. Just my personal opinion on that. So is other dot hypervolume greater than this one's hypervolume. So is that a problem? Is it just because it's not used that's complaining? Definition of a non... Oh, because union is a keyword. That's why. We'll call it all, I guess. So we'll keep track which was so. So if the other one is larger, then this one is smaller. Otherwise, it's the other one. Okay, and so now we need to cut out the intersection from the smaller cube. So although actually we don't even need to, split it up in 7. We can actually like make it considerably smaller than that. So basically, let's see here. So if intersection, well, so we got to go through the dimensions and figure out what to do with each dimension. So d is less than dim plus plus d. So go through each of the dimensions, and if the intersection in this is only partially covers this cube in this dimension, then we need to like slice the smaller cube in that dimension. So if dot if the intersections min should have min point, right? Yeah. It shouldn't be possible. I don't think. Well, you never know. I'm starting to wonder about this, but we'll say like if we'll put a check here, and if this check is wrong, we'll have to slice like more than once. We'll have to slice into 3 pieces in this dimension, but I don't think that's possible with the intersection the way it is. Not 100% sure. We'll find out. Okay. Check intersection. No, it should be less than or equal to there, yeah. The max point should be less than or equal, I think, in that dimension. Okay. So actually, instead of making this just a reference, this is going to be something that we are consistently slicing at. So I'm going to say, I'm actually going to assign it here. So we can do the slice here. So man. It might help myself to draw an example. Well, to like just write out an example here. So like let's say that we have like in the x dimension, you know, well, so like I mean, let's say that we have 2 cubes. We'll only consider the x dimension for now. How about that? We'll only consider 1 dimension, and we have one that goes from 1 to 5, and another that goes from 3 to 10. So their intersection is going to be 3 to 5. And the 3 to 10 we've decided we're keeping. So the 1 to 5 one should be cut down to 1, 2, 3, except that these are inclusive, so it should actually be 1, 2, 2. So using all that as an example, if the intersection's minimum coordinate is greater than I'm just going to clear that out right now because I'm also thinking about other conditions, like let's say, you know, like I mean if in this particular dimension, you know, the intersection covers the full range, then we don't have to cut anything. So like if the intersection were instead, you know, 1 to 5, then we would be keeping 1 to 5. No, we wouldn't though. Would we, or would we? We'd be looking to slice in another dimension then. I don't want subtraction of numeric cubes here. Okay, but let's think of it this way. We want the remaining part of the smaller orthotope in that dimension to cover the range that the intersection does not. So if the intersection so we'll say if smaller dot min point dot chords D is less than intersection min point dot chords D, then there's something that we got to cover there. I'm also realizing that these things are inclusive of max points, but this hypervolume is not exactly like you want it to be. Sorry, just while I'm looking at it, we'll call it hypervolume inclusive const. And that will not be constant, but we'll just have to expand 1 in each direction because, yeah. D equals 0, D is less than dim, plus plus D, diag, dot deltas, D will just increase by 1. And then same accumulation here, multiplying. Okay. All right, back to the union computation. So so we will add to the intersect. So we'll start this slice with the smaller, and then the slice will be one below this, I think. And then smaller. Well, we'll put the slice in the intersection. Not in intersection, in the union. And then the smaller part, we've got, you know, well, we've sliced out one dimension, but it still could extend further in another dimension. So, I mean, we'll say smaller now. Its min point in those coordinates is equal to the min point of the intersection, and then we'll keep on going with the slices, and then and then we have to do the other side of this for max. And we should actually, you know, do that check in here that I was thinking about, that the smaller dot max point there should be greater than or equal to the max point of the intersection, I think. Actually, I'm realizing it's entirely possible now for this to go in multiple directions. So, like, just because of the three-dimensional nature of the problem, yeah. But this can still work, because we'll just check the max size of smaller again, and the smaller will have already had part of it sliced out. So smaller dot max point dot coordinates at D is greater than the max point of the intersection in that dimension, then we'll do another slice. But this time, the min point of that is going to be the max point of the intersection plus 1. And then smaller will now be the max point we're going to confine to the max point of the intersection. And yeah, we should do hypervolume inclusive for these too, I'm realizing now. Because we can have one of these orthotopes that, you know, the min and the max point are the same thing, but because they're inclusive, that still has an inclusive hypervolume of 1 instead of 0. And the inclusive hypervolume is how we're counting how many reactor cells are in this bounding volume. So, okay. So we go through the first dimension, and then at that point, what remains of smaller is totally clamped within the range of the intersection in one dimension. But if it goes, beyond it in another dimension, we get more and more. I think and then maybe if there's still anything left to smaller at the end of this, yeah, we can say if smaller dot hypervolume inclusive ever goes down to 0 or less than or equal. I mean, it shouldn't do that unless we mess up the math, but we'll go ahead and break in case that happens. Then after this, if the remainder contains anything, we will put it in all, put that slice in there. Don't forget to put the slice in here as well. Okay. Then return all. So the math may be wrong in some of these, but once again, we're going to try and test it a little bit. So now, instead of, A and B here, I'm going to have A go to 333 and B go from 1, 1, 1 to, actually 999 is fine. But I want to see now what the union of these is. So we'll just say for these cubes in the union, we will print this stuff out. Try and print this out a little bit nicely. But I am pretty but we'll go ahead and see if the result for union across all those dimensions makes sense. So let's go ahead and do that. So it doesn't. Definitely not from 1 to 9. Well, no, it's union. Sorry, union. It does, I think. So then, putting this all together, we have from origin up to 3, 3 in the x dimension with 0, and then I guess the other way to confirm this is to calculate the total volume, or the hypervolume rather, because we know what that should be. because the total volume here should be the sum of the volumes for the two in the union minus the volume of the intersection. So let's see that, you know, this all, if this all works correctly. So we've got volume of A and volume of B here, 64 and 729, and the intersection is 27. So if we add up this stuff, I'm going to just open a little calculator app here, but we've got 729 plus 16 plus 12 plus 9 plus 27 is 793. And then 729 plus 64 minus 27. So I say, double check that. I might not put that in right. 729 plus 16 plus 12 plus 9 plus 27 is 793. Okay. 729 plus 64 is 793. So we have not subtracted out the inclusive volume here. Do we just need to not put that last, is that last one going to be the same as the intersection? Yeah, because that last one is the same as the intersection. So, I mean, we can actually just check that that is equivalent at the end. Now let's go ahead and define equality for orthotopes and just make sure that that works okay. So we'll say, I'll put that further up actually. Add that check in there and see if that's where we should get to at the end of that run. Okay, so 729 plus 16 plus 12 plus 9, 766. 729 plus 64 minus 27, 766. Okay, that seems okay. If we have like two non-intersecting areas, like we just make this, 444 to 999. There should be nothing for intersections, so we'll just take that part out. We'll just go ahead and look at, it should just give us the two original, which it does. If we have, let's say, like, B is just little skinny in the A direction. Well, so actually, let's say that, if B is fully contained by A, we should just get one back. Which we do. And now if let's say that B is stretchy out in one of those dimensions. Okay. So we've got the original cube A, and then we've got something starting at 114 through 229. I think that looks correct, but let's just do the volume calculations just in case. So we have 64 plus 36 minus 12. So we're shooting for 88. 64 plus 24, also 88. So, okay. So I'm reasonably satisfied that our union calculator is working now. So now we've got everything we need to do to, you know, track a set of cubes that is on, but we also need to be able to track it when they turn off. So, oh, and I hope that, and you know, we might need to, you know, sort some cubes, you know, make this more efficient, because this might, the algorithmic complexity of this, I worry, might kind of blow up, but we shall see. So we need to be able to subtract out something from a cube, and I realize that actually, like, part of what we've already written to do the union of cubes is probably going to be useful for subtraction. So if we do, say, well, so let's go up and do well, it's not exact. Well, it's set difference, kind of. We'll call it spatial difference. And we'll call that sub. So, you know, first we're going to compute the intersection here. And if there's no intersection between the two of them, then we are just going to return this as is, unmodified. No need to mess about with it. If, on the other hand, but if there is an intersection, sorry, it should be if not intersection dot has value, return this. Otherwise, I think it's going to be very similar to this part of the algorithm here, except that we're going to just go from this. So we'll call this remainder. If remainder, and then we'll also have I mean, if the intersection is equal to this, actually. So if the intersection fully covers this cube, then we return nothing, because there is nothing left. It's been completely erased. Um, let's say slices. Uh, changing variable names. This is another, like, really interesting one. It's not, like, fully a stumper that's stopping me, but I really have to think hard about it, and I enjoy that. Okay. So the spatial difference, I think we can actually use with this. So, yeah, well, this we can actually make a const reference now because we're not going to be keep on modifying it, but we'll say smaller dot spatial difference with the intersection and then all dot insert all dot end diff dot begin diff dot end. Okay. So before we even test that spatial difference, I'm just going to rerun this same thing with the new implementation of union that depends partially on that spatial difference and make sure we get, same results, everything looks fine. So for spatial difference now, we'll say, yeah. Yeah, we can still do all that stuff. We'll say A, spatial difference B. What's A with a B-shaped thing cut out of it? So, yeah, that all looks correct as far as the volume math. I think that's pretty good for the spatial difference. Okay, so now we have the primitives that are necessary, I think, to start applying this stuff. Now, it is going to be kind of wild, but we'll see what we can do here. So I'm going to go ahead and comment out all this fun test code that we've been working with. And now we will get to actually writing the proper algorithm for this. So we're going to have a vector of orthotopes. Oh, sorry. Grid 3 orthotopes that are on regions. And then for const procedure and just double check this. The volume calculations are all, yeah, they're all done in int64t. So plenty of headroom. So for each procedure, if okay. The on regions are initially going to be disjoint. So if procedure dot on, then man, we're going to do so much swapping here, but I'm I mean, I guess it depends on how many regions we actually wind up with. Hopefully it's not too out of control, but we'll say so we'll start with the procedures box is obviously going to be on, and then for um, there's going to be ways to optimize this. I'm just trying to. Man, just thinking about the ways that these have to be modified is kind of baking my brain a little bit because you got to do the union with all of the existing regions. Um, and there could be multiple. Well, I mean, there could be multiple cells that are covered by the union. I guess that, I mean, if the problem is being nice to us, then there will only be one other region that we have to consider the union with. But it is, of course, possible that there's more than one. So, who boy, okay. I'm just thinking how to do the union over these whole sets now. So, obviously we can do region dot union of procedure, or just say I wonder if we changed the algorithm for union to always prefer to slice up either to slice up to slice up existing cubes and leave the new region alone. That might make things easier. I mean, so if we go into union here, obviously for or actually, come to think of it, yeah, actually, I like that. I'm kind of liking this now. So we'll say, um, yeah, so this box remainder is going to be whatever's left of the on box from the procedure after we have subtracted out everything that is already on from the on regions. I think this is going to be an easier approach. So we'll initialize that with procedure.box, and then for grid 3 orthotope and region in the on regions. So what we're doing there is we're taking the spatial difference, and then of the whole next remainder, and we'll say then box remainder is the next remainder. So what this is doing is and then we can break out of that early if we've completely gotten rid of it. So what this is doing is we're starting with just the on box from the procedure. We're going through all the existing regions that are turned on. We are subtracting them out from the region covered by that procedure to get this diff. And then we are so you know, we'll just keep slicing stuff out if it's already turned on, and then updating that remainder. And then so finally, if we get to the end here, well, actually we'll just so we get to the end of this, and then on regions we are going to extend. Sorry, that should be on.end by whatever is left of that new stuff to turn on. So that's what we do if procedure if the procedure tells us to turn something on. Otherwise, if the procedure tells us to turn something off, then we just need to subtract out the off region from everything. So we'll just say standard vector grid 3 next on regions region spatial difference with the box from the procedure. And put that into the end of the next on regions, and then we'll say on regions is next on regions. Okay. And then finally, to calculate how much is on, we just add together, and all these on regions, no matter what, are going to be disjoint, the way that we've written it. So then we just sum together the inclusive hypervolumes of all the on regions. So hypervolume inclusive, spit out total on. Entirely possible that we have made horrible mistakes up to this point, but let's just go ahead and run it with our input and see what it gives us. Let's see if it finishes in a reasonable amount of time. The other thing that I worry about is that this, okay, it did not chew up as much time as I thought it was going to, which is nice. Let's see if this is correct. All right, and came in just under 1,000 on today's leaderboard. Good for us. So yeah, looking at personal stats, you know, the first star we were a little slow on, but second one we got there, you know, relatively well, under 1,000. So this was another problem. This was another puzzle that was like big about geometry, and really figuring out what that we need. I'm sorry, my mic may have just glitched there for a second. Apologies, because I knocked the cord there. But this was another geometry problem, and I think that figuring out how to take orthotopes or hyperrectangles, or is it? I'm not sure if cuboid is the right word. I'm not up on all my terminology, but basically to take these three-dimensional regions of space and be able to cut and to be able to like cut them out from each other, and you know, figure out like unions and intersections, like working out the 3D geometry was the first tough part of that. And then you know, once we're able to do that math on these sort of hyper rectangles, then we get to a point here. Yeah, that's fine. Then we get to a point where you know, we write this actual algorithm here, and so we keep track of, you know, all that's turned on, and I think what slowed me down a little bit was thinking about, you know, how to apply union here, and do we need to apply union with everything? But then I realized, just instead of trying to union the on region, the new on box from the procedure with all the previous on regions and expand that out, like if you flip that problem on its head and you say, okay, there's going to be this new on region from the procedure, but if I subtract out everything that's already on, the remainder is the stuff that's newly on, and we can just put that in the on regions. And that makes it, you know, at least it made it easier for me to get my head around it computationally. And then the turning stuff off is relatively simple. You just need to do the spatial difference and subtract everything out. So yeah, I mean, this this year of advent of code, I think, has in many ways been the year of geometry, and thinking about things spatially. kind of like 2 years ago, the solar system puzzles. Well, I mean, there's were kind of like the year of like machine simulation. We had that int code machine, and there's always some pathfinding stuff too. But yeah, I'm pretty happy with where we got tonight. I mean, you saw me kind of like struggle through thinking about um, these solid geometry problems, but if we kind of like take it one dimension at a time, um, thinking about it and reasoning from there, and think, okay, well, first let's figure out how to do intersections, then let's how to figure out how to exploit the ability to do intersections to do union and spatial difference, then we really get to something cool. So I might even extend dimension grid even farther to like um, have to be able to represent a set of orthotopes that is just kind of like in arbitrary arbitrary multiple volumes in space. Um, but we'll see. For now, I'm pretty good with the solution. I'm gonna go ahead and upload it to the GitHub repository, and we're gonna call it a night. So thank you all for watching the stream. This was another difficult but fun problem. I hope you enjoyed watching me work through it. If you are watching the live stream on Twitch, you can go ahead and check the channel description, and there you're going to find a link to my YouTube channel where we have replays of all the live streams throughout Advent of Code, as well as a link to the GitHub repository where I upload all of the code that we write. If, on the other hand, you're watching on YouTube, go ahead and check that video description right down there, and there you will find links to the Twitch channel for the live streams, and once again to the GitHub repo where all of that code lives. Thank you very much for joining me tonight and working through this puzzle. I hope you had fun, and I hope to see you again tomorrow night. Bye-bye.